Hey guys, tonight we begin with something a little different. We're not talking about plagues or emperors or ancient tombs. Tonight we're going back further than any of that, way further. We're traveling roughly 375 million years into the past to a world that would be completely unrecognizable to you. A world of shallow swamps, suffocating heat, and a biological nightmare that makes your worst Monday look like a vacation. Tonight's story is about fish, but not the kind you see gliding peacefully in aquariums or the kind you order grilled with lemon and rice. These were fish in crisis. Fish living in a dying world. Fish forced to make one of the most brutal evolutionary gambles in the history of life on Earth. They had to grow legs. And let me tell you, it wasn't some magical Disney transformation where a cheerful narrator sings about dreams coming true. It was messy. It was painful. It took millions of years of trial, error, and catastrophic failure, and the vast majority of them didn't make it. Before you get too comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what we're doing here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's drifting off to evolutionary drama at 3 a.m. versus who's winding down after dinner in another time zone entirely. Now, dim the lights. Maybe turn on a fan for that soft background hum. Get yourself settled in because tonight we're crawling out of the water together, one agonizing mutation at a time. And trust me, by the time we're done, you're going to be very grateful you're already lying down in a world where breathing air is easy, where gravity doesn't crush you, and where your skin doesn't need to stay wet just to keep you alive. So let's ease into this journey, back to a time before footsteps, before lungs that worked properly, before anything even remotely resembling the comfortable existence you're experiencing right now. Back to when being alive meant constantly fighting just to stay that way. This is the story of why it absolutely sucked to be a fish growing legs. And spoiler alert, your ancestors were those fish. Every single one of them. The ones who made it, anyway. Picture this. Earth, 375 million years ago. The Devonian period. A time so alien, so fundamentally different from the world you know, that if you were dropped there for even 5 minutes, you'd probably panic. There are no trees, no grass, no birds singing in the morning, no mammals scurrying through underbrush, because none of those things exist yet. The land is almost entirely barren, a rocky, muddy expanse of volcanic stone and primitive moss. The world is hot. Not summer vacation hot, not even desert hot. We're talking about a planet with carbon dioxide levels roughly 10 times higher than today, creating a greenhouse effect that turns much of the Earth into a sweltering, humid nightmare. The atmosphere is thick, heavy, and if you tried to breathe it, you'd immediately notice something wrong. The oxygen content is lower than what you're used to, hovering around 15% compared to the 21% you're breathing right now without even thinking about it. But here's the thing. You wouldn't be worried about the land, because all the action, all the life, all the drama of existence is happening in the water. Shallow seas stretch across vast portions of the continents. Enormous reef systems, built not by coral but by strange armored fish and primitive marine creatures, dominate the ocean floors. And in the coastal areas, in the tidal zones and estuaries, that's where our story begins. The Devonian is often called the Age of Fishes, and for good reason. Fish have exploded into an incredible diversity of forms. There are armored fish called placoderms, some as small as your hand, others as large as modern great white sharks, their heads encased in bony plates like medieval knights. There are early sharks, sleek and efficient, already perfected by millions of years of evolution. There are lobe-finned fish, strange creatures with muscular fins that look almost like stubby arms, pushing themselves along the bottom of murky pools. These fish rule the world. They're the apex predators, the bottom feeders, the filter feeders, the scavengers. They occupy every available niche in the aquatic ecosystem. If you could dive into these ancient waters, you'd see a riot of bizarre forms: fish with scissor-like jaws, fish with sucker mouths, fish with fins like paddles, fish with eyes on stalks. It's an evolutionary experiment on a massive scale, and for the moment, it's working beautifully. But there's a problem brewing, a big one, and it's going to force some of these fish to make a choice they probably would have preferred to avoid: leave the water or die. See, the Devonian climate is unstable, violently so. Seasonal droughts sweep across the continents with regularity. What was a thriving freshwater lake in the wet season becomes a shrinking, oxygen-starved puddle in the dry season. Fish that thrived in deep water suddenly find themselves trapped in pools barely deep enough to cover their backs. The water temperature spikes, the oxygen content plummets, and the competition for what little breathable water remains becomes desperate. Imagine being a fish in one of these shrinking pools. You're surrounded by hundreds, maybe thousands of other fish, all of you gasping, all of you struggling. The water is thick with algae, turning it green and soupy. Dead fish float on the surface, their bodies already beginning to rot in the heat. The smell, if you could smell it, would be overwhelming. Decay, sulfur, stagnant vegetation. And every day, the water level drops a little more. Some fish die quickly. They simply can't adapt. Their gills are designed for oxygen-rich water, and when that oxygen disappears, they suffocate. It's not peaceful, it's not gentle. They thrash, they struggle, and then they stop moving. Others have a slight advantage. They can gulp air at the surface. It's not efficient, and it's certainly not comfortable, but it buys them time. A few more hours, a few more days. But time for what? The pool is still shrinking. The drought isn't ending. And beyond the water's edge lies an environment even more hostile. Dry land, baking under a merciless sun, offering no food, no moisture, and no obvious way to move or breathe. This is the crisis. This is the evolutionary pressure cooker that's about to change everything. Because in this impossible situation, a few fish, a very small percentage of the population, have something the others don't. Not intelligence, not planning, not foresight, just a random mutation. Maybe their fins are slightly more muscular. Maybe their swim bladder has a little more surface area for gas exchange. Maybe their skin can tolerate air exposure for a few seconds longer. These tiny advantages mean nothing in good times, but in a drought, when the water is gone and death is certain, these mutations become the difference between extinction and survival. Not because these fish want to leave the water, but because staying in it is no longer an option. The world before legs wasn't a world of opportunity. It was a world of desperation. And what's about to happen next, this awkward, painful crawl onto land, isn't triumph. It's just the least terrible option left. So now that you understand the nightmare these fish are living in, let's meet the poor creature that's about to become your ancestor. Meet Tiktaalik. Your great, 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 and we're talking about 1 billion greats here, grandparent, discovered in the Canadian Arctic in 2004, this fossil changed everything we thought we knew about the transition from water to land. And when you see what it looked like, you'll understand why scientists got so excited, and also why you might feel a little uncomfortable about your family tree. Tiktaalik lived roughly 375 million years ago, right in that sweet spot, or maybe more accurately, that terrible spot when fish were being forced out of the water. It was about 9 feet long, roughly the size of a large crocodile, and it looked like something drawn by a committee that couldn't agree on whether they were designing a fish or a lizard, because honestly, it was both, and neither. From the back, Tiktaalik looked like a fish. It had scales, it had fins, it had a tail designed for swimming. Its body was streamlined, built for moving through water with the efficiency of millions of years of aquatic evolution behind it. If you only saw its rear half, you'd think, okay, that's definitely a fish. But then you'd see the front half, and that's where things get weird. Tiktaalik had a flat, crocodile-like skull. Its eyes sat on top of its head, not on the sides like most fish, which meant it was designed to look up to see above the water's surface. It had a neck, an actual, functional neck, which fish don't have. Fish can't turn their heads independently of their bodies, but Tiktaalik could. It could look around, track movement, scan its environment like a predator that spent time in shallow water where visibility mattered. And then there were the fins. Oh, the fins. Because Tiktaalik's front fins weren't really fins anymore. They were proto-limbs. Inside those fins were bones, honest-to-goodness bones, that correspond almost exactly to the bones in your arm right now. A humerus, the upper arm bone, a radius and ulna, the 2 bones in your forearm. And even the beginning of a wrist structure, primitive but undeniable. These fins had joints. They could bend, they could rotate, and most importantly, they could bear weight. Tiktaalik could do something most fish absolutely cannot do. It could push itself up. It could lift its body off the ground, prop itself on those muscular front limbs, and drag itself forward. Not gracefully, not quickly, but it could move on land, even if only for short distances. Imagine that for a second. You're a fish. You've spent your entire evolutionary history gliding effortlessly through water, supported by buoyancy, moving in 3 dimensions with flicks of your tail. And now, because your pool is drying up and you're desperate, you're flopping onto mud, using fins that weren't designed for this, dragging your body like a sack of wet sand, every movement exhausting, every breath a struggle. But here's the thing. It worked. Not well, not comfortably, but Tiktaalik and creatures like it could survive out of water for short periods. They could haul themselves from one shrinking pool to another. They could escape predators trapped in drying puddles. They could access food sources, insects and worms that other fish couldn't reach. And in a world of droughts and mass die-offs, that ability, however clumsy, was the difference between leaving descendants and becoming a fossil with no legacy. Tiktaalik wasn't alone. There were other transitional species around the same time. Panderichthys, slightly earlier, already showing the flattened body and upward-facing eyes. Acanthostega, slightly later, with actual digits, fingers, though still spending most of its time in water. These creatures represent a spectrum, a gradual transition, each generation slightly more adapted to the impossible task of living between 2 worlds. And here's where it gets personal. Because you, yes you, listening to this while lying in bed, carry the genetic legacy of these creatures. The bones in your arms and legs are modified versions of the bones in Tiktalik's fins. The structure is the same: one bone, two bones, many bones, digits, your inner ear bones, the tiny ones that let you hear, evolved from the gill arches of fish. Your jaw, the way it hinges and moves, is a modified fish jaw. Even the way you swallow, the muscular contractions in your throat, those are inherited from gill-pumping mechanisms. Scientists didn't just guess at this. They traced it through fossils, through embryology, through DNA. When you're developing in the womb, you briefly have structures that look like gill slits. They don't become gills, of course. They become parts of your face and neck. But the blueprint is there, written in genetic code that's been passed down for hundreds of millions of years, copied and modified, but never entirely erased. So when you look at a fossil of Tiktaalik, you're not looking at some distant, irrelevant creature. You're looking at family, weird, scaly, gasping for air in a Devonian swamp family, but family nonetheless. And that creature, awkward and desperate as it was, is the reason you exist, because it survived long enough to reproduce, and its descendants survived, and their descendants survived. An unbroken chain of survival stretching across 375 million years, leading directly to you. It's humbling, really. You share more than 90% of your DNA with a fish. You share body structures, developmental patterns, even some basic behaviors. You are, in a very real sense, a modified fish. A fish that learned to walk, to breathe air, to regulate its own temperature, to think complex thoughts, but still, at your core, built on a fish chassis. So the next time you're at an aquarium, staring at some ancient-looking fish in a tank, remember, you're not that different. You're just the version that made it onto land. And that transition, that brutal, grinding, evolutionary shift, is what we're about to explore in excruciating detail. Because Tiktaalik may have had the tools to survive on land, but that doesn't mean it was easy. Not even close. And the first problem it faced, the most immediate crisis, was something you never think about: breathing. You probably don't think much about breathing. Right now, as you're lying there listening to this, your lungs are working automatically. You're pulling in air, extracting oxygen, expelling carbon dioxide, and doing it all without conscious effort. It's so easy, so natural, that you only notice it when something goes wrong, when you're congested or out of breath or holding your breath underwater. But for Tiktaalik and its relatives, breathing was never easy. It was a constant, exhausting crisis. Let's start with the problem: water. Specifically, water that's running out of oxygen. In a healthy, aquatic ecosystem, oxygen dissolves into water from the atmosphere and from photosynthesizing plants and algae. Fish extract that dissolved oxygen using gills, thin membranes with massive surface area that allow gas exchange. Water flows in through the mouth, passes over the gills, and exits through slits on the sides of the head. It's elegant, efficient, and it works beautifully as long as the water has enough oxygen in it. But in a Devonian drought, that system collapses. As pools shrink and temperatures rise, oxygen solubility drops. Warm water holds less dissolved oxygen than cold water. It's basic chemistry, and it's a death sentence for most fish. Add to that the explosion of algae in stagnant water, algae that dies and decomposes, consuming even more oxygen in the process. Add the decay of dead fish, the metabolic waste of hundreds of desperate creatures packed into a shrinking space, and you've got water that's essentially suffocating everything in it. Fish gills are incredibly efficient in oxygen-rich water, but in oxygen-poor water, they're useless. It's like trying to breathe through a straw while someone's holding a pillow over your face. You can try all you want, but you're not getting what you need. And so fish in these dying pools do the only thing they can. They swim to the surface and gulp air. Now, most fish can't process air. Their gills collapse when exposed to it. Gills are designed to work in water, where the thin membranes are supported by liquid. In air, they stick together like wet paper, losing almost all their surface area. It's the aquatic equivalent of your lungs filling with fluid. You can try to breathe, but it doesn't work, and so most fish that gulp air get nothing from it. It's a desperate, pointless gesture, a final attempt before suffocation. But Tiktaalik wasn't most fish. Tiktaalik had something that gave it a slight, critical advantage, a modified swim bladder. Now, swim bladders are common in fish. They're gas-filled sacs that help with buoyancy, allowing fish to adjust their depth without constantly swimming. Most fish fill them with oxygen extracted from their blood or gulped from the surface, then use them purely for flotation. But in some fish, these swim bladders have extra blood vessels, more surface area, and the ability to absorb oxygen directly from the air inside them. In other words, they function as primitive lungs. Not good lungs, not efficient lungs, but lungs nonetheless. And in a world where the water is poison and the surface offers the only breathable oxygen, even bad lungs are better than no lungs at all. So picture Tiktaalik in its shrinking pool, surrounded by dying fish. It swims to the surface, breaks through with its flat, crocodile-like head, and gulps. Air rushes into its mouth, travels down into the swim bladder/lung, and oxygen slowly, painfully slowly, diffuses into the bloodstream. It's inefficient. A mammal would look at this system and laugh. But it works. Barely. Just enough. But here's the problem. Tiktaalik still has gills. It still needs water. It can supplement its oxygen intake with air breathing, but it can't abandon the water entirely. Its gills still provide most of its gas exchange. Its skin, thin and permeable, still handles some respiration. And most critically, its gills are how it expels carbon dioxide. Breathing air into a primitive lung gives you oxygen, sure, but it doesn't solve the waste gas problem. Carbon dioxide builds up in the blood, acidifying it, causing stress and eventually death if it's not removed. So Tiktaalik is stuck. It needs air to get oxygen, but it needs water to get rid of carbon dioxide. It's living in two worlds, fully adapted to neither, constantly managing a biochemical balancing act that would kill most creatures outright. Every breath is a negotiation. Every gulp of air is followed by a return to water, gills flaring, trying to dump waste gases before the next desperate surface trip. And this isn't a temporary situation. This is life now. For millions of years, these transitional creatures exist in this horrible middle ground. They can't go back to being fully aquatic because the water keeps drying up. But they can't fully commit to land because their respiratory system isn't ready. They're trapped in an evolutionary limbo, breathing just well enough to not die immediately, but never comfortably, never easily. Think about what that means. Imagine if every breath you took required conscious effort. If you had to coordinate between two different systems, one for intake, one for expulsion, and if you got the timing wrong, you'd suffocate. Imagine if sleeping meant constantly waking up to gasp for air, to reposition yourself, to make sure you're still getting enough oxygen to keep your brain alive. That's the reality for these creatures. Rest is dangerous. Sleep is barely possible. Survival is a full-time job. And this is just the breathing problem. We haven't even talked about what happens when these creatures try to move on land, when gravity stops being a gentle suggestion and becomes a crushing, inescapable force. But we will, because as bad as the oxygen crisis was, the structural nightmare of supporting your own weight was somehow even worse. So, you've got a swim bladder that's trying its best to be a lung. Congratulations. You can gulp air at the surface and absorb a little oxygen before you suffocate. But here's the thing nobody tells you about evolutionary compromises. They're messy, inefficient, and often more painful than the problem they're trying to solve. Welcome to the nightmare of growing lungs while you're still drowning. Let's talk about what a swim bladder actually is. In most fish, it's a smooth, oval sac filled with gas, sitting just above the digestive system. Its job is buoyancy control. Fish can adjust the gas volume to rise or sink in the water column without wasting energy swimming. It's elegant, simple, and it works beautifully for what it's designed to do. But lungs? That's a completely different engineering problem. Lungs need surface area. Lots of it. The more surface area, the more contact between air and blood, the more efficient the gas exchange. Human lungs, if you could unfold all the tiny air sacs inside them, would cover roughly the area of a tennis court. That's how you get enough oxygen into your bloodstream to power a brain, muscles, and all the metabolic processes that keep you alive. A smooth swim bladder has almost no surface area. It's like trying to absorb water with a bowling ball instead of a sponge. So the swim bladder has to change. Over millions of years, over thousands of generations, it develops folds, pockets, and little subdivisions that increase its internal surface area. Blood vessels proliferate, spreading across these new structures like roots searching for water. The walls thin out, allowing gases to diffuse more easily. What was once a flotation device is slowly, painfully, becoming a respiratory organ. But this transformation doesn't happen overnight. It doesn't even happen over thousands of years. It happens across millions of years of incremental mutations, most of which do nothing, some of which are actively harmful, and a tiny few of which provide just enough advantage to get passed on to the next generation. And during all that time, these creatures are living with lungs that barely work. Imagine breathing through a plastic bag. You can do it, technically. Air goes in, some oxygen gets absorbed, carbon dioxide accumulates, and eventually you pass out or rip the bag off your face. That's what early lung breathing was like. Tiktaalik gulps air, and maybe 10, maybe 15% of the oxygen in that gulp actually makes it into the bloodstream. The rest just sits there, useless until the next gulp. There's no efficient flow, no continuous exchange like you have with every breath you're taking right now. And here's another problem. Control. Your breathing right now is automatic, regulated by your brainstem, adjusted constantly based on carbon dioxide levels in your blood. You don't think about it. You don't have to. But Tiktaalik's proto-lung system has no such automation. It has to consciously gulp. It has to return to the surface. It has to coordinate mouth movements, throat contractions, and the opening and closing of gill flaps to force air into the right place. One mistake, one poorly timed gulp, and it's inhaling water into a structure that absolutely cannot handle it. Because here's the cruel irony. While Tiktaalik is developing the ability to breathe air, it still needs water. Its gills are still the primary respiratory organ. They're still pulling most of the oxygen it needs when the water has any oxygen to give. But gills and lungs have opposite requirements. Gills need to stay wet. Lungs need to stay dry, or at least not flooded. Managing both simultaneously is like trying to stay warm and cool at the same time. You're constantly compromising, constantly adjusting, never quite comfortable in either state. And let's talk about what happens when things go wrong. Water in the lungs, even primitive lungs, is a disaster. Unlike gills, which are designed to have water flowing over them, lungs rely on air-filled spaces. Water is heavy, roughly 800 times denser than air. If those spaces flood, they collapse. The surface area vanishes. Gas exchange stops. And unlike choking on land, where you can cough and expel the obstruction, a fish with flooded lungs has limited options. It can try to force the water out, but the mechanisms for doing that are crude at best. Infections are another nightmare. Lungs, even primitive ones, are warm, moist environments connected directly to the outside world. Bacteria, fungi, parasites, they all love that. And Tiktalik's immune system, evolved for dealing with aquatic pathogens, isn't prepared for the kinds of organisms that thrive in air-exposed tissue. Respiratory infections in these early land-venturing creatures were probably common, debilitating, and often fatal. Then there's the energy cost. Breathing with gills is passive. Water flows over them as the fish swims or as it pumps water through its mouth. But breathing with lungs, especially inefficient proto-lungs, requires active effort. Muscles have to contract. The mouth has to open and seal. The throat has to expand and compress. Every breath costs energy, and these creatures are already operating on razor-thin metabolic margins. They're starving in shrinking pools, fighting for scraps of food, and now they have to spend precious calories just to breathe. So why do it? Why go through all this suffering, this biological chaos, this constant risk of drowning on air or suffocating in water? Simple, because the alternative is worse. The pools are drying up, the oxygen is gone, and fish that can't breathe air, even badly, even painfully, are already dead. They're floating on the surface, rotting in the sun, feeding the few survivors who can still move, still breathe, still cling to life for one more day. Tiktaalik and its relatives aren't thriving, they're barely surviving. Every generation is a gauntlet of suffocation, starvation, and predation. But they're alive, and their lungs, terrible as they are slowly getting better. More surface area, more blood vessels, more efficiency. Not because evolution is kind or forward-thinking, but because the ones with slightly better lungs live long enough to reproduce, and the ones with worse lungs don't. It's brutal, it's random, and it's the only reason you're able to lie in bed right now, breathing easily, oxygen flooding your bloodstream without any effort at all. Because 375 million years ago, some desperate fish choked on air, survived, and passed that ability down through an unbroken chain of descendants that eventually, impossibly, became you. But breathing was just the beginning. Because once you can survive on land for more than a few seconds, you encounter an even more fundamental problem. Your fins aren't feet, and gravity is about to remind you of that in the most painful way possible. Your fins are becoming limbs, and it hurts. Not the kind of hurt where you pulled a muscle at the gym or slept wrong and woke up with a stiff neck. We're talking about deep, structural, bone-level changes happening over thousands of generations, each one a tiny step towards something that barely works, each one accompanied by a cascade of failures, deformities, and deaths. Let's start with what a fin actually is. Fish fins are essentially skin stretched over thin, flexible rays made of bone or cartilage. They're lightweight, streamlined, and perfect for moving through water. They provide thrust, steering, and stability. But they're not built to bear weight. They're not meant to push against solid ground. They're designed for a medium that supports you, cradles you, lets you glide with minimal effort in 3 dimensions. Legs, on the other hand, are weight-bearing structures. They need thick bones, strong joints, powerful muscles, and the ability to generate force against a surface that doesn't give. Walking, even badly, requires your limbs to support your entire body mass against gravity, and gravity, as any fish leaving the water quickly discovers, is not negotiable. So how do you get from fin to leg? You might imagine some dramatic moment, some single mutation that changes everything. But that's not how evolution works. Evolution is blind, random, and achingly slow. What actually happens is this. A fish is born with slightly thicker bones in its fins. Not because it's supposed to have thicker bones, just because DNA copying isn't perfect and sometimes you get variations. Most of the time, those variations do nothing. Sometimes they're harmful, but occasionally, in a world where you need to drag yourself across mud to reach the next pool, thicker bones mean you don't break your fin on the first push. That fish survives. It reproduces. Some of its offspring inherit those thicker bones, and a few of those offspring are born with even thicker bones, or maybe with a slightly different angle where the fin attaches to the body, or with more muscle tissue around the base. These aren't improvements in any grand sense. They're just random changes that happen to be useful in this one specific, horrible situation. Over millions of years, these changes accumulate. Fins get more muscular. The bones inside them start to differentiate, forming distinct segments. What was once a continuous fan of rays becomes something more jointed, more segmented. The shoulder girdle strengthens, shifting from a delicate structure meant to anchor a fin into something robust enough to transfer force from the body to the ground. But here's the thing that nobody talks about. All those intermediate stages are worse than what came before. A fin that's halfway to being a leg is bad at being a fin and bad at being a leg. It's too heavy for efficient swimming. It's too weak for effective walking. It's a compromise that satisfies neither function, and the creatures stuck with these in-between appendages are suffering for it. Imagine trying to walk on your elbows. That's essentially what early limb-bearing fish are doing. Their proto-legs stick out sideways from their bodies, not underneath like yours do. They can't stand upright. They can't stride. They can only sprawl on their bellies and push, dragging their bodies forward with awkward, lurching movements that exhaust them within seconds. And the bones, oh, the bones are failing constantly. These early limbs aren't designed for the stress they're under. The joints aren't properly articulated. The bone density isn't sufficient, so bones crack, joints dislocate, cartilage tears. Every time one of these creatures hauls itself onto land, it's risking structural failure. And in a world without medical care, without rest, without any option but to keep moving or die, a broken limb is usually a death sentence. You can see evidence of this in the fossils. Paleontologists have found specimens with healed fractures, malformed joints, and signs of chronic stress injuries. These weren't rare occurrences. They were the norm. Every fish trying to use its fins as legs was accumulating damage. Some died from it. Others survived just long enough to reproduce, passing on their slightly better but still terrible limb structure to the next generation, is less than #0. 7 is greater than. Then there's the muscle problem. Fish muscles are designed for quick, powerful contractions in short bursts. That's perfect for darting away from predators or lunging at prey in water, but walking requires sustained, controlled contractions. You need endurance, not just power. And the muscle fibers in these transitional creatures aren't built for that. They fatigue quickly, they cramp, they tear under prolonged strain. So these early land venturers can only move for a few seconds at a time before they have to rest. A journey that would take you 30 seconds to walk might take them an hour, with frequent collapses, gasping breaths, and desperate moments of wondering if they'll have the strength to reach the next pool or if they'll simply die on the mud, exposed to the sun, unable to move. And let's not forget the coordination problem. Your brain has a sophisticated motor cortex dedicated to controlling your limbs. You can walk without thinking about it. You can climb stairs, jump, run, all with automatic, practiced precision. But these creatures don't have that. Their nervous systems evolved for controlling fins, not limbs. Every movement is conscious, clumsy, uncertain. They're learning to walk with hardware that isn't designed for the task. It's like trying to type with your feet. Technically possible, but incredibly difficult, frustratingly slow, and prone to constant mistakes. Now imagine your life depends on your typing speed, and you'll start to understand the desperation these creatures are experiencing. But again, the ones with slightly better limbs, slightly better muscle endurance, slightly better neural control, those are the ones that make it to the next pool. Those are the ones that find food. Those are the ones that survive long enough to reproduce. And slowly, painfully, over millions of years and countless generations, fins become limbs. Not because it's easy, not because it's elegant, but because it's just barely possible. And barely possible is enough when the alternative is extinction. So yes, your arms and legs, the ones you're probably not even thinking about right now as you lie comfortably in bed, those are the result of millions of years of broken bones, torn muscles, and exhausted creatures dragging themselves through mud because they had no other choice. Every joint, every tendon, every carefully articulated bone structure is built on a foundation of suffering. And if you think the limbs had it bad, wait until we talk about what gravity does to the rest of the body. Because weight-bearing limbs are just the beginning of the structural nightmare. Gravity is not your friend. Right now, as you're lying down, gravity is gently pressing you into your mattress. It's a comfortable, even pleasant sensation. Your spine is supported, your muscles are relaxed, your body weight is distributed across a soft surface designed specifically to make gravity bearable. But stand up, and suddenly gravity becomes work. Your leg muscles engage, your core stabilizes, your heart has to pump harder to move blood upward against gravitational pull. And you don't even notice because your body has been designed by millions of years of evolution to handle this exact problem. Tiktalik's body was not designed for this problem, not even close. For its entire evolutionary history, stretching back hundreds of millions of years, its ancestors lived in water. And water is a miracle substance when it comes to supporting body weight. Water is dense, roughly 800 times denser than air, which means it provides buoyancy. A fish in water is essentially weightless. It doesn't need strong bones to hold itself up. It doesn't need powerful muscles to fight gravity. It just floats, moves, exists in 3 dimensions without ever thinking about which way is down. But air provides no buoyancy, None. When Tiktaalik drags itself onto land, every single gram of its body weight is suddenly pressing down on whatever parts are touching the ground. And for a creature that's 9 feet long and probably weighs somewhere between 50 and 90 kilograms, that's a catastrophic amount of force concentrated on limbs and a skeletal structure never meant to bear it. Let's put this in perspective. Imagine you spent your entire life in a swimming pool. You could move effortlessly, twist, turn, flip, all without strain. Your muscles would be lean and adapted for gliding, not lifting. Your bones would be light, just strong enough to anchor muscles and protect organs, but not built like load-bearing pillars. Now imagine someone drains the pool and tells you to walk. Suddenly, your legs have to support your full weight. Your spine has to stay rigid against the crushing downward force. Your muscles, completely unprepared for this, scream in protest within seconds. That's what Tiktaalik is experiencing every single time it leaves the water. Its body, built for neutral buoyancy, is suddenly being compressed by its own mass. The belly, normally suspended in water, now drags on the ground. The internal organs, which in water spread out comfortably in the body cavity, now pile onto each other under gravitational pressure. The spine, a flexible structure designed to undulate for swimming, now has to become a rigid beam supporting the entire torso without collapsing. And it's not like this problem resolves quickly. Tiktaalik's spine is made of vertebrae that are fine for swimming but terrible for weight bearing. The vertebrae are relatively flat, stacked like coins, with lots of cartilage between them for flexibility. That's perfect in water. On land, it's a disaster. The cartilage compresses under load, the vertebrae shift, the whole structure wants to buckle, to sag in the middle like a bridge made of rubber. So the spine starts accumulating damage, compression fractures, herniated discs, or rather, the Devonian equivalent of herniated discs. Chronic inflammation, where bone grinds against bone under stress it was never meant to handle, and there's no rest. There's no physical therapy. There's no painkiller. The creature just has to live with it, move through it, survive despite it. Then there's the rib cage. In water, ribs are mostly for protecting organs and providing attachment points for muscles. They're light, flexible, and they don't need to be particularly strong. But on land, ribs have an additional, critical function. They help you breathe. When you inhale, muscles pull your ribs outward and upward, expanding your chest cavity, creating negative pressure that draws air into your lungs. It's a mechanical system that requires ribs rigid enough to maintain structure but flexible enough to move. Tiktaalik's ribs aren't built for this. They're too flexible, too weak. So breathing on land is even harder than it needs to be because the rib cage can't create efficient negative pressure. Every breath requires more effort, more muscle contraction, and delivers less oxygen. It's like trying to inflate a balloon that has a hole in it. You can do it, but it's exhausting and inefficient. And let's talk about what gravity does to circulation. Your heart right now is working against gravity to pump blood to your brain. When you stand up quickly, sometimes you get lightheaded because your cardiovascular system needs a moment to adjust the pressure and make sure your brain gets enough oxygen. You have specialized valves in your veins, regulatory mechanisms in your arteries, and a whole suite of adaptations to make sure blood goes where it needs to go, regardless of your position. Tiktaalik has none of that. Its circulatory system is designed for horizontal living. The heart pumps blood forward and backward, not up and down. So when it hauls itself onto land and lifts its head, blood pools in the lower parts of its body, the brain gets less oxygen, vision dims, Coordination falters. It's a constant battle to maintain consciousness, to keep the brain supplied while gravity is doing everything it can to drain blood away from it. Compound this with the fact that Tiktaalik is already hypoxic, already struggling to get enough oxygen from its primitive lungs, and you have a creature that's perpetually on the edge of passing out. Every movement is slow, cautious, because moving too fast might mean losing consciousness, and losing consciousness on land, exposed and vulnerable, is usually fatal. The internal organs are suffering too. In water, organs are packed efficiently but loosely in the body cavity, suspended in fluid, gently supported on all sides. On land, they sag. The liver, the stomach, the intestines, all of them press downward, compressing the organs beneath them. Digestion becomes harder. Waste elimination becomes more difficult. Everything internal is being squeezed, shifted, stressed in ways it never was in water. And there's the simple, brutal reality of pressure sores. When you lie in one position too long, your skin and the tissue beneath it get compressed between bone and whatever surface you're on. Blood flow decreases. Cells start dying. You develop sores, painful and prone to infection. Now imagine you're a fish with delicate skin lying on rough, abrasive mud or stone, unable to shift your weight properly because your limbs are too weak. Pressure sores develop quickly, break open, and become infected. An infection, in a world without antibiotics, without any medical intervention at all, is often a slow death sentence. So every minute Tiktaalik spends on land, its body is being crushed, damaged, strained beyond its design limits. It's not adapting in real time, it's just enduring. And the ones that endure slightly better, the ones with slightly stronger spines, slightly better circulation, slightly tougher skin, those are the ones that survive long enough to pass on their genes. Gravity isn't just an inconvenience. It's a relentless, inescapable force that's breaking these creatures down with every second they spend out of water. And yet, they keep going. Because back in the water, there's no oxygen, and suffocation is worse than crushing, barely, but worse. And if you thought gravity was the worst part of being on land, just wait until we talk about what happens to your skin when it dries out. Your skin is trying to kill you. Well, not your skin exactly. You're fine. Your skin is a marvel of evolutionary engineering. Waterproof, self-healing, covered in helpful bacteria, equipped with temperature regulation and sensory networks that would make any engineer weep with envy. But Tiktaalik's skin? That's a different story. Because Tiktaalik's skin can't decide if it's supposed to work in water or air. And that indecision is turning every moment on land into a slow-motion disaster. Let's start with what fish skin actually is. Fish skin is thin, permeable, and covered in a layer of mucus. That mucus isn't just slime for the sake of being slimy. It's a critical protective barrier. It helps with hydrodynamics, reducing friction as the fish moves through water. It protects against parasites and bacteria. And in many species, it actually assists with respiration. Some fish can absorb up to 30% of their oxygen directly through their skin. It's an elegant system, perfectly adapted for an aquatic life. But the moment that skin hits air, everything breaks down. Air is dry. Compared to water, even humid air is a desiccating wasteland. And mucus, that wonderful protective layer, starts evaporating immediately. Within seconds, the skin begins to dry out. The mucus layer thins, cracks, and loses its protective properties. The skin beneath it, never meant to be exposed, starts losing moisture at a catastrophic rate. For Tiktaalik, this is an emergency. Fish skin is permeable because it needs to be. In water, that permeability allows gas exchange, waste removal, and osmotic balance. But on land, permeability means water is escaping from your body into the air, constantly, unstoppably. It's like trying to carry water in a sieve. You can try all you want, but you're losing it faster than you can replace it. And dehydration for a fish out of water isn't a slow decline. It's rapid and brutal. Within minutes, cells start malfunctioning. The blood thickens. The heart has to work harder to pump increasingly viscous fluid through narrowing vessels. Organs that depend on fluid balance, basically all of them, start failing. The eyes dry out. The gills, still present and still essential, stick together and stop functioning. The whole body begins shutting down. So Tiktaalik can't stay out of water for long. Even with its primitive lungs, even with its muscular fins turning into legs, it's on a countdown timer every time it leaves the pool. 10 minutes, maybe 15 if it's lucky and the air is humid, and then it has to get back to water or die of dehydration. It's like being on a leash made of your own biology, constantly pulled back to the one environment where your skin can function. But here's where it gets worse. The skin isn't just losing water, it's also cracking. Dry skin becomes brittle. It splits, especially around joints and areas of flexion. Every time Tiktaalik bends its proto-limbs to drag itself forward, the skin stretches, and in places where the mucus has dried out, it tears. Not deep cuts, not yet, but micro tears that expose the tissue beneath to air, to bacteria, to all the dangers of an environment the immune system isn't prepared for. These micro tears hurt, they sting, and more importantly, they become infection sites. The bacteria that live in Devonian swamps are not friendly. Some are decomposers, actively breaking down dead organic matter, and they're not picky about whether that organic matter is completely dead or just damaged. They colonize the cracks in the skin, multiply rapidly in the warm, moist tissue beneath, and start causing infections that the fish's immune system struggles to fight. And let's talk about scales. Most fish have scales, hard, overlapping plates that provide protection and structure. Tiktaalik has scales too, but they're a problem now. Scales are rigid, they don't flex well. In water, that's fine because the body is supported and movements are smooth. But on land, where the body is bending, scraping, dragging across rough surfaces, scales catch on things. They dig into the skin beneath them. They trap moisture, creating pockets where bacteria can thrive. And in some places, they break off entirely, leaving raw, exposed patches of skin that bleed and invite infection. So over millions of years, scales start to change. In the lineage that will eventually lead to amphibians and then to you, scales become smaller, thinner, and eventually disappear almost entirely. But that transition takes time. For thousands of generations, these creatures are stuck with scales that are too rigid for land life, but too essential to lose completely. Another compromise, another source of constant discomfort. Then there's the mucus gland problem. Fish produce mucus constantly, automatically. It's a passive system. But on land, where mucus evaporates in minutes, the glands have to work overtime. They produce more, faster, trying to keep up with the rate of loss. And like any biological system pushed beyond its design limits, they start failing. Some glands overproduce, creating thick, sticky mucus that actually makes movement harder. Others underproduce, leaving dry patches. Still, others become inflamed, infected, or blocked entirely. And here's a detail that's particularly miserable. Mucus production requires water. Your body has to pull water from somewhere to make mucus. So the more mucus Tiktaalik produces to protect its drying skin, the faster it dehydrates internally. It's a vicious cycle. Protect the skin, dehydrate the organs. Stop producing mucus, let the skin crack and bleed. There's no winning, only degrees of losing. Now, eventually, evolutionary pressure will push some of these lineages toward developing actual waterproof skin. Layers of keratin, specialized cells that prevent water loss, adaptations that will make land life sustainable, but that's millions of years away. Right now, in the Devonian, these creatures are stuck with skin that's desperately trying to do two incompatible jobs and failing at both. And if the skin dries too much, even for a few minutes too long, it's not just uncomfortable, it's lethal. The sensory nerves in the skin, exposed and raw, send pain signals constantly. The body interprets this as a crisis, flooding the system with stress hormones. The heart rate spikes, energy reserves burn faster, and all of this is happening in a creature that's already exhausted from fighting gravity, struggling to breathe, and desperately searching for food in an environment it's barely equipped to navigate. So Tiktaalik and its relatives live in a constant state of emergency. Every trip onto land is a calculated risk. Stay too long and the skin fails. Return to water too soon and you might not have found food or reached a better pool. The margin for error is razor thin, and most individuals don't get it right. They dry out, crack, bleed, and die on the mud, their bodies adding to the smell of decay that hangs over every shrinking pool. But the ones that manage it, the ones whose skin holds out just long enough, whose mucus glands work just a little bit better, those are the ones that survive. And over time, imperceptibly, slowly, the skin adapts, not by choice, not by design, but by the simple, brutal logic of evolution, work or die. And speaking of things trying to kill you, let's talk about what happens when you're finally on land, skin barely holding together, and you realize you have no idea what to eat or how to catch it. You've made it onto land, your lungs are barely working, your limbs are exhausted, your skin is cracking, and now you realize something truly terrible. You're starving, and everything you know about finding food, everything your ancestors perfected over millions of years of aquatic evolution, is completely useless here. Welcome to the nightmare of eating on land when your entire body is designed for hunting in water. Let's start with what Tiktaalik ate in the water. Most likely, it was a predator, using those sharp teeth to catch smaller fish, crustaceans, and anything else slow or unlucky enough to come within striking distance. Hunting underwater is all about speed, surprise, and hydrodynamics. You drift slowly, conserving energy, then explode forward in a burst of acceleration. Water resistance does most of the work of slowing you down afterward. Your lateral line, that sensory organ running along your sides, detects pressure changes from nearby prey. You don't even need to see your target. You can feel it moving through the water. But on land, none of that works. There's no water to carry pressure waves. Your lateral line, that amazing piece of evolutionary engineering, is useless in air. You're essentially blind to prey unless you can see it or hear it, and your vision is blurry because your eyes are designed for the refractive index of water, not air. Everything looks wrong, distorted, harder to judge for distance. And even if you spot something edible, catching it is a completely different problem. In water, you can approach from any angle, three-dimensional ambush predation at its finest. On land, you're stuck on a two-dimensional surface. You can't dive down or rise up. You're belly flat, exhausted, barely able to drag yourself forward. Your prey, meanwhile, is probably an arthropod, an insect, or a millipede, or a primitive scorpion, and those things are fast. They skitter, they jump, they disappear into cracks in the mud before you can even lunge. So Tiktaalik has to learn an entirely new hunting strategy. And learning, in evolutionary terms, means thousands of failed attempts, thousands of starving individuals, and the rare success that keeps the species alive. The ones that figure it out, through luck more than skill, are the ones that reproduce. The rest die hungry. Let's talk about the mouth. Fish mouths are built for suction, feeding, or biting in water. Tiktaalik probably used a combination of both. Open the mouth rapidly, create negative pressure, suck the prey in along with a rush of water, then close the jaws and expel the water through the gills while keeping the food inside. It's efficient, elegant, and completely dependent on being submerged. On land, suction feeding doesn't work. There's no water to create the pressure differential. You can't suck air and expect prey to come with it. So now the mouth has to function purely as a mechanical trap. You have to bite down, grab the prey with your teeth, and hold on. Sounds simple, right? Except Tiktaalik's jaw muscles are weak for this kind of work. They're built for quick snaps in water, not sustained gripping pressure in air. And the teeth, those sharp, backward-pointing teeth perfect for holding slippery fish, aren't ideal for terrestrial prey either. Arthropods have exoskeletons, hard shells made of chitin that don't compress easily. Biting down on a beetle is nothing like biting down on a soft-bodied fish. The teeth might penetrate, or they might just slide off the hard carapace. And if the prey struggles, if it kicks with those spiny, segmented legs, it can actually injure the inside of the mouth. Then there's the problem of chewing. Fish don't chew, they swallow prey whole or in large chunks. Their digestive systems are built to handle this. Strong stomach acids break down flesh, bones, scales, everything. But arthropod exoskeletons are tougher. They're made of a polymer that resists acid degradation. Swallowing a beetle whole means you're ingesting a tough, fibrous shell that your stomach might struggle to break down efficiently. So over time, evolutionary pressure will favor jaws that can crush, grind, and process food before swallowing. But again, that's millions of years away. Right now, Tiktaalik is choking down hard-shelled prey and hoping its digestive system can handle it. Sometimes it can, sometimes it can't. Intestinal blockages, perforations, malnutrition despite eating, all of these are risks. And let's not forget that Tiktaalik isn't the only predator trying to make a living on land. The Devonian shoreline is home to some truly nightmarish creatures. These aren't the tiny scorpions you might find under a rock today. These are armored, aggressive predators with crushing claws and venomous stingers. They're faster in water than Tiktaalik, better armored, and they're also starting to venture onto land during high tides. Then there are the eurypterids and other massive arthropods, some of which are experimenting with terrestrial life just like the fish are. And unlike Tiktaalik, their bodies are already somewhat suited for land. Their exoskeletons provide structure and protection. Their jointed legs can bear weight more efficiently than proto-limbs. They're not comfortable on land, not yet, but they're less miserable than the fish trying to compete with them. So Tiktaalik barely able to move, half-blind, wheezing through primitive lungs, is now competing with creatures that are faster, better armored, and more experienced at terrestrial hunting. It's not a fair fight. Most of the time, Tiktaalik loses. It watches prey escape. It gets chased away from food by larger predators. It expends precious energy on failed hunts and gains nothing. Starvation is slow. It's not dramatic. You don't just collapse and die immediately. First, your body starts burning fat reserves. Then it moves to muscle tissue. Your movements become weaker, slower. Your brain, deprived of glucose, starts functioning poorly. Decision-making deteriorates. Reaction time increases. You become less able to hunt, which means you become more hungry, which makes you even weaker. It's a downward spiral that's almost impossible to reverse without a significant food intake. And food on land, in the Devonian, is scarce and difficult to catch. The terrestrial ecosystem is still in its infancy. There are no forests, no complex food webs, just primitive plants, arthropods, and a few desperate fish trying to make the transition. Competition is fierce, resources are limited, and the margin between survival and starvation is almost non-existent. But somehow, some of these creatures figure it out. They learn to hunt slower prey. They develop better jaw strength. They adapt their digestive systems to handle new types of food, not because they're smart or determined, but because the ones that randomly happen to be slightly better at it live long enough to pass on their genes. The ones that don't die hungry on the shore, their bodies picked clean by scavengers, their lineage ending in silence. So every meal you eat, every effortless trip to the refrigerator, every time you order takeout and have food delivered directly to your door, remember this: your ancestors fought for every single calorie. They starved, they failed, they died trying to eat things their bodies weren't designed to process. And the only reason you're here is because a tiny fraction of them succeeded. But even if you manage to find food and somehow choke it down, there's another biological crisis waiting. Because eating is one thing, reproducing in a world that's trying to kill you is something else entirely. You've survived the drought. You've learned to breathe air, even if it hurts. You've dragged yourself across land on limbs that weren't designed for it. You've found food, barely, and kept yourself alive long enough to reach sexual maturity. And now your body is telling you it's time to reproduce. Congratulations. This is about to become the most complicated, frustrating, and ultimately heartbreaking part of your existence. Let's talk about how fish reproduce, because it's actually beautifully simple. Most fish practice external fertilization. The female releases eggs into the water. The male releases sperm into the water. They meet, they fuse, and embryos start developing. No physical contact required. No elaborate courtship beyond some color displays and territorial posturing. The water does all the work, carrying gametes, providing a medium for the sperm to swim through, cushioning the developing eggs. It's efficient, it's low energy, and it produces massive numbers of offspring. A single female fish can release thousands, sometimes millions of eggs in one spawning event. Most of those eggs won't survive. They'll be eaten, fail to fertilize, or die from environmental stress. But a few will make it, and that's enough to keep the species going. It's a numbers game, and in water, it works. But Tiktaalik is spending more and more time on land. No cushioning for delicate eggs. Reproduction on land should be impossible, and for the most part, it is. That's why Tiktaalik and its descendants never fully abandon water. They can't. Not yet. Not for millions of years. Because they're still chained to aquatic reproduction. So here's what has to happen. No matter how far these creatures venture onto land, no matter how well adapted they become to terrestrial life, they have to return to water to breed. Every single generation. It's not optional. It's not something they can evolve past quickly. The entire reproductive system, from gamete production to embryo development, is locked into an aquatic framework that takes tens of millions of years to modify. This means that even the most terrestrial individuals, the ones who've spent weeks on land hunting and exploring, have to crawl back to the pools when mating season arrives. And those pools, remember, are the same shrinking, oxygen-depleted, predator-filled death traps they've been trying to escape. But biology doesn't care about irony. If you want to reproduce, you go back to the water. Now let's talk about the eggs themselves. Fish eggs are small, numerous, and entirely dependent on being submerged. They have no shell, no protective barrier beyond a thin membrane. They absorb oxygen directly from the surrounding water. They're permeable, which means they maintain osmotic balance with their environment. In water, this works perfectly. The embryo develops, hatches, and swims away as a tiny larva. But on land, or even in very shallow water, these eggs are doomed. If the water level drops even slightly, the eggs are exposed to air. And air, as we've established, is a desiccating nightmare. The eggs dry out within minutes. The embryos inside die, their cells collapsing as water evaporates through the permeable membrane. There's no coming back from that. A dried egg is a dead egg. So the parents have to choose their spawning sites very carefully. They need water that's deep enough to stay wet, but shallow enough to be warm, because embryos develop faster in warm water. They need water with enough oxygen to support the developing embryos, but not so much current that the eggs get swept away. And they need water that's relatively safe from predators, which is almost impossible because every pool is teeming with things that eat eggs. Even under ideal conditions, the survival rate is abysmal. Most eggs are eaten within hours of being laid. Some fail to fertilize. Others develop abnormally and die before hatching. And many, perhaps most, simply run out of oxygen as the pool they're in becomes stagnant and hypoxic. The parents lay thousands of eggs because they have to. 99% won't make it. And the parents? They don't stick around to protect the eggs. They can't. They've expended enormous energy just getting back to the water, finding a mate, and spawning. Now they need to eat, to recover, to prepare for the next drought cycle. Parental care, the kind you see in birds and mammals, doesn't exist yet. You lay your eggs, hope for the best, and leave. If any survive, great. If not, well, you try again next year. If you survive that long. But here's where it gets even more complicated. The larvae that do hatch are fully aquatic. They're tiny, vulnerable, gill-breathing fish with no capacity for air breathing or land movement. They're starting from scratch, evolutionarily speaking. All the adaptations their parents developed for terrestrial life, the stronger limbs, the primitive lungs, the tougher skin, none of that is present in the larvae. They have to grow into it. This is called metamorphosis, and it's going to become a defining feature of amphibian life. You start as an aquatic larva, basically a fish, and gradually transform into a more terrestrial adult. But transformation takes time, energy, and resources. The larva has to eat constantly, grow rapidly, and somehow avoid being eaten long enough to complete the process. Most don't. They're eaten by adult fish, by insects, by their own siblings. Cannibalism is common when food is scarce and you're surrounded by easy, nutritious prey that happens to be your brother. And even if a larva survives to adulthood, it's emerging into the same hostile world its parents struggled through. The same droughts, the same predators, the same impossible balancing act between water and land. Nothing has gotten easier. The cycle just repeats, generation after generation, each one barely clinging to survival. This is one of the cruelest aspects of evolution. You can't skip steps. You can't just decide to lay eggs that work on land because that would be convenient. The physiology has to change incrementally over millions of years through countless failed experiments. Eventually, some lineages will develop the amniotic egg, a self-contained life support system with its own water supply, waste storage, and protective shell. That egg will be one of the most important innovations in the history of life on Earth. It will free vertebrates from dependence on aquatic reproduction and allow true terrestrial life. But that's 50 million years in the future. Right now, in the Devonian, reproduction is a leash that drags every land-venturing creature back to the water. You can't escape it. 2. You can't evolve past it quickly. You're trapped in a life cycle that requires both environments, and if either one fails, if the land becomes too hostile or the water disappears entirely, your entire species goes extinct. Prisoners of their own biology, forced to return to the place they're trying to escape, forced to reproduce in the exact conditions that are killing them, forced to watch their offspring struggle through the same nightmare they endured. There's no triumph here, just survival, barely, and the grim hope that maybe the next generation will have it slightly less terrible. But even if you solve reproduction, even if your eggs somehow survive and your larvae grow into adults, there's still the problem of experiencing the world around you, because your senses, every single one of them, are about to betray you in ways you can't even imagine. Your world has just gone silent and blurry and confusing in ways that make your brain hurt because everything you evolved to sense, everything your nervous system was built to detect and interpret, just stopped working the moment you left the water. Welcome to sensory deprivation and overload happening simultaneously. A neurological nightmare that makes every moment on land disorienting, dangerous, and exhausting. Let's start with your lateral line, because losing it is like losing half your brain. The lateral line is a sensory organ that runs along both sides of a fish's body, a series of tiny hair cells encased in fluid-filled canals just beneath the skin. These cells detect pressure changes in the surrounding water. When another fish swims nearby, when a predator approaches, when prey moves in the darkness, the lateral line feels it. It's not hearing, not exactly, and it's not touch, but something in between. It's how fish navigate in murky water, how they school in perfect synchronization, how they hunt in complete darkness. In water, the lateral line makes you almost omniscient. You can sense movement in a 360-degree radius. You don't need to see a predator behind you. You feel the pressure wave it creates just by moving. You can detect the flutter of a smaller fish's tail from meters away. You can sense the current, the contours of rocks and plants, the presence of other creatures, all without looking, all automatically, all the time. But air doesn't carry pressure waves the same way water does. Air is too thin, too light. The lateral line, that miracle of aquatic sensory evolution, becomes useless the moment you emerge onto land. It's like going deaf, except worse. Because you're losing a sense humans never had, a sense you depended on for literally everything. Suddenly, the world behind you doesn't exist. You can't feel movement, you can't sense approach. You're vulnerable in ways you've never been vulnerable before. So Tiktaalik on land is constantly anxious, constantly turning its head, which it can do, unlike most fish, but it's exhausting. Every sound, every movement in your peripheral vision becomes a potential threat because you can't feel your environment anymore. You're navigating through sensory static, trying to piece together a picture of your surroundings using only vision and whatever primitive hearing you have, and neither of those is working properly either. Let's talk about vision. Water and the lens of the eye have similar refractive indices, which means light bends at a very specific angle as it enters the eye, focusing precisely on the retina. It's a system that works beautifully in water, but air has a completely different refractive index. Light bends differently, and Tiktaalik's eyes, optimized for aquatic vision, can't adjust. Everything on land looks wrong, blurry, distorted, like you're trying to see through a smudged window. Distance perception is off. Objects appear closer or farther than they actually are. Movement is harder to track because your visual system keeps trying to compensate for refractive properties that don't exist in air. You're functionally nearsighted, and there's no optometrist to give you corrective lenses. And your eyes are drying out. Fish eyes are constantly bathed in water. They don't need eyelids or tear ducts because the environment provides all the moisture they need. But in air, the surface of the eye starts to dry within seconds. It stings. It clouds your vision even more. You try to blink, except you don't have eyelids yet, not functional ones. Some early tetrapods develop a nictitating membrane, a thin, translucent layer that can slide across the eye, but it's crude, inefficient, and doesn't really solve the problem. So you're squinting, trying to keep your eyes moist, trying to see clearly, and failing at both. Hunting becomes even harder. Avoiding predators becomes nearly impossible. You're stumbling through a blurry, silent world where threats can appear from anywhere and you won't know until it's too late. Now, let's talk about hearing, or rather, the lack of it. Fish don't have external ears. They don't need them. Sound travels efficiently through water, and fish detect it using their inner ear structures and, again, that lateral line. But in air, sound behaves completely differently. It's quieter, for one thing. Air is less dense than water, so it carries sound waves with less energy. What would be a loud noise underwater is barely audible in air. Tiktaalik has inner ear structures, yes, but they're not designed for airborne sound. They're tuned for detecting vibrations through water and substrate. So hearing in air is muffled, unclear, almost useless. You can detect loud, low-frequency sounds, maybe, but high-frequency noises, the kind that might warn you of an approaching predator, those just don't register. Over millions of years, some of those inner ear bones will be repurposed. The higher mandibular, a bone that in fish helps support the jaw and gill apparatus, will migrate and become the stapes, one of the tiny bones in your middle ear that transmits sound vibrations. It's one of the most elegant examples of evolutionary repurposing in the fossil record. But right now, in the Devonian, that hasn't happened yet. Tiktaalik is functionally deaf in air, stumbling through silence broken only by the loudest, most obvious sounds. And then there's the sense of smell. Fish smell through their nostrils, but those nostrils aren't connected to the mouth or throat. They're separate structures that pull water in, pass it over olfactory receptors, and expel it. Smell underwater is incredibly acute. Fish can detect chemical concentrations in parts per billion. They can smell blood from kilometers away. They navigate by scent, find food by scent, identify mates by scent. But scent in air is different. Molecules disperse more slowly, hang in the air longer, but also require different receptor sensitivities. Tiktaalik olfactory system is designed for aquatic chemistry, not airborne molecules. So smelling on land is vague, imprecise, frustrating. You catch hints of scent, but you can't track it reliably. You can't tell if the smell is fresh or hours old. You can't determine direction as easily. Another sense, degraded and unreliable. So put it all together. You're on land, you can't feel your environment because your lateral line is useless. You can't see clearly because your eyes are blurry and drying out. You can't hear effectively because your ears are tuned for water. You can't smell reliably because your olfactory system is confused by airborne molecules. You're navigating through a sensory void, trying to hunt, trying to avoid predators, trying to survive, and you're essentially blind, deaf, and numb compared to what you were in water. It's disorienting in a way that's hard to describe. Imagine waking up one day and 3 of your 5 senses just stopped working properly. You could still technically function, but everything would be harder, slower, more dangerous. You'd be exhausted from the constant mental effort of trying to compensate. That's what every moment on land is like for these creatures. Is less than #0. 7 hash is greater than, and yet, somehow, they adapt. Not quickly, not easily, but over millions of years, sensory systems evolve. Eyes develop lids and tear ducts. Ears repurpose bones for airborne sound detection. The brain rewires itself to prioritize vision and hearing over the now absent lateral line input. It's a slow, agonizing process, paid for in the deaths of countless individuals who couldn't adapt fast enough. But we're not done with the suffering yet, because even if you could see, hear, and smell properly, there's still the problem of temperature. And in the Devonian, temperature isn't just uncomfortable, it's lethal. You're cold. No, wait. Now you're hot. Actually, you're cold again. And this isn't the kind of temperature fluctuation where you adjust the thermostat or add a blanket. This is your core body temperature, swinging wildly between hypothermia and heat stroke, sometimes within the same hour, and there's absolutely nothing you can do about it except try not to die. Welcome to life without internal temperature regulation, where the sun dictates whether you're functional or slowly cooking from the inside out. Let's start with a basic fact about fish. They're ectothermic, cold-blooded in common language. Though that term is misleading because their blood isn't actually cold. What it means is that their body temperature matches their environment. If the water is 15 degrees Celsius, so are they. If it's 25 degrees, they warm up accordingly. And in water, this system works beautifully because water temperature is stable. It changes slowly, predictably, seasonally. A fish can adjust its behavior, moving to deeper or shallower water to find its preferred temperature range. But air temperature is chaos. Water has high thermal mass. It absorbs and releases heat slowly, buffering against rapid changes. Air has almost no thermal mass. It heats up fast in sunlight and cools down just as fast when the sun sets. In the Devonian, with its extreme greenhouse climate, daytime temperatures on land could easily reach 40 to 45 degrees Celsius or higher. At night, especially in higher latitudes or during seasonal shifts, temperatures could plunge to 10 or 15 degrees. That's a 30-degree swing in 12 hours. And Tiktalik's body temperature swings right along with it because it has no mechanism to regulate itself internally. No metabolic furnace generating heat from within, no sweat glands or panting reflex to cool down, no shivering to generate warmth. Just a body that passively matches whatever temperature the environment imposes. So let's talk about what happens when you get too cold. As body temperature drops, chemical reactions slow down. Enzymes, the proteins that catalyze every single metabolic process in your body, become less efficient. At optimal temperatures, enzymes work quickly, breaking down food, producing energy, repairing damage. But as temperature falls, those reactions crawl. Your metabolism slows, energy production drops, muscles become sluggish, unresponsive. For Tiktalik on a cold morning, this means waking up essentially paralyzed. Its muscles are stiff, barely functional. It can't move quickly. It can't hunt. It can't even drag itself back to water if it needs to. It's stuck, waiting for the sun to rise, for the air to warm, for its body temperature to climb back into a functional range. And during that time, it's vulnerable. Predators that are slightly warmer, slightly more active, can attack with impunity. But waiting for warmth comes with its own risks. As the sun climbs higher, as the rocks and mud heat up under direct sunlight, the temperature doesn't just rise to comfortable. It keeps going. 40 degrees, 45, maybe higher in exposed areas. And now Tiktaalik is overheating. Its body temperature is climbing into dangerous territory, and unlike you, it can't sweat, it can't pant, it can't do anything to cool itself down except move. So it has to find shade. It has to drag itself to a cooler spot, maybe under a rock outcropping, maybe back toward the water. But movement generates more heat. Muscles contracting produce thermal energy as a byproduct, so the act of trying to escape the heat makes you hotter. It's a vicious cycle, and if you're too far from shade or water, you simply cook. Your proteins denature, your cells start dying, your brain function deteriorates. You collapse, unable to move, and if the temperature doesn't drop soon, you die of hypothermia. Your body literally cooked by the sun. This is why early tetrapods are crepuscular. They're most active at dawn and dusk, the narrow windows of time when temperatures are moderate enough for their bodies to function without risk of freezing or overheating. Midday is for hiding, midnight is for waiting. Life becomes a series of brief activity windows, separated by long periods of forced inactivity. And here's the thing about being ectothermic. You can't think your way out of it. When you're cold, your brain slows down too. Decision-making becomes impaired. Reaction time increases. You become dopey, sluggish, almost drunk. When you're too hot, the brain overheats. Neurons misfire. You become confused, disoriented, incapable of complex thought. So you can't even strategize about temperature management when you need it most. Behavioral thermoregulation is all these creatures have. Bask in the sun to warm up. Retreat to shade to cool down. Bury yourself in mud to insulate against temperature extremes. Huddle with others to share warmth. Though that's risky because it also means sharing space with potential competitors or threats. Every behavior is a trade-off, a calculated risk, and most of the time, you're getting it wrong. Let's talk about what this means for energy. Endothermic animals, warm-blooded creatures like you, maintain a constant internal temperature by burning calories continuously. It's expensive, metabolically speaking. You need to eat a lot to fuel that internal furnace, but the advantage is consistency. You can be active at any time, in any temperature, as long as you have food. Ectothermic animals use far less energy. When it's cold and they're inactive, their metabolic rate drops to almost nothing. They can survive for weeks without food because they're barely burning calories. That's an advantage in a world where food is scarce. But the disadvantage is that they're slaves to the environment. They can't be active when it's too cold or too hot. They can't hunt at night. They can't escape predators if the temperature is wrong. So Tiktaalik and its relatives are stuck in this constant struggle. They need warmth to move, but too much warmth kills them. They need to hunt, but only during narrow temperature windows. They need to avoid predators, but their ability to flee depends entirely on whether the sun is out. It's exhausting, not physically in the moment, but over time, the stress accumulates. The near misses with temperature extremes take their toll. And sleep? Forget about it. You can't sleep comfortably when your body temperature is swinging. You can't enter deep, restorative sleep when you might freeze or overheat at any moment. Sleep becomes fragmented, shallow, constantly interrupted by the need to adjust position, seek better microclimates, or simply wake up because your body is too cold or too hot to maintain unconsciousness safely. This is one of the cruelest aspects of ectothermy. You're always tired. You're always either too sluggish to function or too overheated to rest. There's no comfortable middle ground, or if there is, it lasts maybe an hour or two per day. The rest of the time, you're enduring, not living, waiting for conditions to improve just enough that you can move, eat, and try to survive one more day. Eventually, some lineages will evolve endothermy. They'll develop the ability to generate and regulate their own body heat, freeing themselves from environmental temperature constraints. But that's 100 million years away, and it comes with its own enormous costs. Right now, in the Devonian, temperature is a tyrant. It dictates every aspect of life, and there's no escape from its rule. But even temperature, brutal as it is, isn't the worst internal problem these creatures face. Because while the outside of their body is struggling with heat and cold, the inside, specifically the heart and circulatory system, is trying to do a job it was never designed for, and it's failing in ways that would terrify any cardiologist. Your heart is confused. It's trying to pump blood through a system that's being asked to do two completely incompatible things at once, and the result is a cardiovascular nightmare that leaves you perpetually exhausted, oxygen-starved, and one step away from complete circulatory failure. Welcome to the problem of having a fish heart in a body that's trying not to be a fish anymore. Let's start with the basics. A fish heart has two chambers. One atrium that receives deoxygenated blood from the body, and one ventricle that pumps that blood to the gills. Simple, elegant, efficient. The blood flows in a single loop, heart to gills, where it picks up oxygen, gills to body, where it delivers that oxygen to tissues, body back to heart, where the cycle repeats. It's a single circuit system, and it works beautifully as long as you're getting all your oxygen from gills. But Tiktaalik isn't getting all its oxygen from gills anymore. It's also gulping air and absorbing oxygen through its primitive lungs. And here's the problem. Lungs and gills require completely different blood flow patterns. Gills need a continuous stream of deoxygenated blood so they can oxygenate it. Lungs need the same thing. But if you're sending deoxygenated blood to both at the same time through a single circuit system, you're splitting the flow. Neither organ gets enough blood, neither functions efficiently. Even worse, once blood gets oxygenated, whether from gills or lungs, it immediately mixes back together with deoxygenated blood in the heart. There's no separation. Oxygen-rich blood from the lungs flows into the same atrium as oxygen-poor blood returning from the body. They mix, and what gets pumped out is a compromise, not fully oxygenated, not fully deoxygenated, just mediocre blood that satisfies nothing. This is catastrophically inefficient. Your tissues need oxygen. Your brain especially needs oxygen. But they're receiving blood that's only partially oxygenated because the heart can't separate the two streams. So you're always slightly hypoxic, always functioning below optimal capacity, always tired in a way that sleep can't fix because the problem isn't fatigue. The problem is that your cells literally aren't getting enough oxygen to produce energy efficiently. Now, evolution is going to solve this problem eventually. Over millions of years, the heart will add a third chamber. The atrium will divide into two separate chambers, one for deoxygenated blood coming from the body, one for oxygenated blood coming from the lungs. This creates a partial separation that improves efficiency dramatically. Amphibians today have this three-chambered heart, and it's a significant upgrade from the two-chambered fish heart. But even a three-chambered heart isn't perfect. The ventricle, the pumping chamber, is still single. So, while incoming blood is partially separated, it still mixes somewhat when it gets pumped out. You get better oxygenation than a fish? Yes, but not as good as what you have right now with your four-chambered heart, where oxygenated and deoxygenated blood are completely separated and never mix. And that four-chambered heart, that's another 50 million years of evolution away. Right now, Tiktaalik is stuck with a two-chambered heart trying to do a three-chambered heart's job, and it's struggling. Every heartbeat is inefficient. Every circulation cycle delivers less oxygen than the tissues need. The whole system is running at maybe 60 or 70% efficiency, and that deficit adds up fast. Let's talk about blood pressure, because that's another crisis. In fish, blood pressure is relatively low. It doesn't need to be high because water supports the body and blood doesn't have to fight gravity to reach the brain. But on land, gravity is pulling blood downward constantly. If you lift your head, blood wants to pool in your lower body. Your brain, sitting at the highest point, gets whatever's left over after gravity has taken its cut. Tiktaalik's heart isn't strong enough to generate the pressure needed to overcome gravity effectively. So when it lifts its head, which it needs to do to look around, to breathe air, to function on land, blood flow to the brain decreases, vision dims, consciousness wavers. It's like standing up too fast and getting lightheaded, except it's happening constantly, every time the head is elevated. The solution, eventually, will be a more powerful heart, thicker ventricular walls, higher blood pressure, and a suite of regulatory mechanisms to manage that pressure. But again, that's millions of years away. Right now, these creatures are stuck with low blood pressure, poor circulation to the brain, and a constant risk of passing out from something as simple as looking up. And here's another problem: exercise. When you exercise, your muscles need more oxygen. Your heart rate increases, your blood pressure rises, and your cardiovascular system delivers that oxygen efficiently to where it's needed. You can sustain activity for extended periods because your four-chambered heart and well-developed circulatory system can meet the demand. But Tiktaalik's cardiovascular system can't scale up effectively. When it tries to move, when it drags itself across land or struggles to escape a predator, its muscles demand more oxygen. The heart beats faster, yes, but it's still pumping that same inefficient, partially oxygenated blood. The demand increases, but the supply doesn't keep pace. Lactic acid builds up in the muscles. Fatigue sets in almost immediately. Within seconds, the creature is exhausted, gasping, unable to continue. This is why early tetrapods move in short bursts. They can't sustain activity. They lunge, drag, rest, repeat. It's not a choice. It's a limitation imposed by a cardiovascular system that wasn't built for terrestrial locomotion. Every movement is anaerobic, burning through energy reserves that can't be replenished fast enough because oxygen delivery is inadequate. And let's talk about what this means for sleep, because it's genuinely terrible. Sleep requires your body to enter a restorative state where heart rate slows, blood pressure drops, and systems repair themselves. But if your cardiovascular system is already barely keeping up during waking hours, what happens when it slows down during sleep? Oxygen delivery drops even further. The brain, already operating on thin margins, gets even less of what it needs. So sleep becomes shallow, fragmented, unsatisfying. You can't enter deep sleep because your brain keeps waking you up, sensing hypoxia, triggering arousal responses to make you breathe more, move more, do something, anything to increase oxygen intake. It's like sleep apnea, except you don't have apnea. You're breathing fine. The problem is that your cardiovascular system is so inefficient that even normal breathing isn't enough to maintain adequate oxygenation during rest. This chronic sleep deprivation compounds every other problem. You're already struggling to move, to hunt, to avoid predators. Now add constant fatigue from poor quality sleep. Decision-making deteriorates further. Reaction times slow. Immune function drops, making infections more likely. Stress hormones remain elevated because your body never truly rests. It's a downward spiral that most individuals don't escape. And the heart itself? It's working overtime, constantly, never getting a break. The cardiac muscle is under perpetual strain, trying to pump blood through a system that's too complex for its simple two-chambered design. Over time, the heart muscle thickens, not in a healthy way, but in a pathological way. It becomes less efficient, more prone to arrhythmias, more likely to simply fail. Cardiac failure in these creatures is probably common. The heart gives out, not from a sudden event like a heart attack, but from chronic exhaustion. It just stops being able to generate enough force to circulate blood. The creature becomes lethargic, unable to move, and eventually dies as its tissues suffocate from lack of oxygen despite the lungs and gills still technically functioning. This is one of the most fundamental problems with transitional forms. Every system in the body is designed to work together as an integrated whole. When you start changing one system, like adding lungs for air breathing, you create cascading problems in other systems that weren't designed to accommodate that change. The heart, the blood vessels, the regulatory mechanisms, they all have to evolve in parallel, and that takes time. Millions of years of time. And during all that time, every generation is living with mismatched systems that barely function together. So yes, Tiktaalik has lungs, but having lungs without a circulatory system designed to support them is almost worse than not having lungs at all. It's a promise of improvement that never quite delivers, a biological tease that keeps you alive just long enough to suffer more. But even with all these physical failures, with all these systems breaking down, some of these creatures survive. Not many, not most, but enough. And those survivors, those lucky few, are the reason you're here. They're also a reminder of something important. Survival doesn't mean success. Sometimes it just means you suffered less than everyone else. For every Tiktaalik that made it, for every creature that managed to drag itself from one pool to another and survive long enough to reproduce, there were thousands that didn't. Tens of thousands, maybe millions. The fossil record shows us the winners, the successful experiments, the lineages that continued, but it doesn't show us the overwhelming majority of attempts that ended in failure, in death, in genetic dead ends that vanished without leaving a trace. Let's be clear about what evolution actually is. It's not a process with a goal. It's not intelligent. It's not trying to create better organisms or move life towards some predetermined outcome. Evolution is simply this. Random mutations occur, most do nothing, some are harmful, and a tiny fraction happen to be useful in a specific environment at a specific time. The individuals with useful mutations survive slightly more often, reproduce slightly more successfully, and pass those mutations on. That's it. That's the entire mechanism. So when we talk about fish developing legs, we're not talking about fish that wanted legs or needed legs in some conscious sense. We're talking about fish born with random skeletal variations. Most of those variations were useless or actively harmful. A fin bone that's too thick makes swimming harder. A fin bone that's too thin breaks under stress. A joint that bends the wrong way provides no advantage and might even cause injury. But in a drought, in a shrinking pool, when the only option is to drag yourself across land to reach another water source, suddenly a fin bone that's slightly thicker, slightly more robust, becomes the difference between reaching that pool and dying in the mud halfway there. Not because it's a good design, just because it's slightly less terrible than the alternative. The fossil record from the Devonian is full of experiments that didn't work. Species that developed elaborate armor but couldn't move efficiently. Species with powerful jaws but weak limbs. Species with strong limbs but inadequate respiratory systems. Each one represents a lineage that tried, that survived for a few generations, maybe a few thousand years, and then went extinct when conditions changed or when a competitor with a slightly better combination of traits outperformed them. Take Acanthostega, a creature that lived slightly after Tiktaalik. It had legs, actual legs with digits, 8 toes per foot, in fact, but its legs were weak, probably not capable of supporting its weight on land. Its ribs were too short and straight to support terrestrial locomotion. Its tail was still equipped with a fish-like fin. Acanthostega was more adapted for life in water than Tiktaalik was. Despite having more advanced limbs, it represents a branch of the evolutionary tree that went in a different direction, a direction that ultimately didn't lead to fully terrestrial life. That entire lineage is extinct. Or consider Ichthyostega, another early tetrapod with functional legs but a body that was still fundamentally aquatic. It had a strong spine, good for supporting weight, but its hips weren't well connected to the spine, meaning it couldn't transfer force efficiently from its legs to its body. It probably moved on land by dragging itself forward with its front limbs while its back limbs and tail provided some assistance. It's an awkward, inefficient design, and while Ichthyostega survived for millions of years, its lineage also eventually died out. These weren't failures in the sense that they did something wrong. They were just experiments that didn't happen to be in the right place at the right time with the right combination of traits. Evolution doesn't care about effort. It doesn't care about how hard you try. It only cares about reproduction. If you reproduce before you die, you win. If you don't, your genetic line ends, and it's as if you never existed. Now, think about the math. In any population, mutations are rare. A typical mutation rate might be 1 mutation per 100 million base pairs per generation. The fish genome is large, roughly 1 billion base pairs, so each individual might carry a handful of new mutations. Most of those mutations are in non-coding DNA and do nothing. Of the ones that do affect proteins or regulatory genes, most are neutral or harmful. Maybe 1 in 10,000 mutations is beneficial, and beneficial is context dependent. A mutation that helps in a drought might be useless or harmful in times of plenty. So you need a large population, reproducing over many generations, just to generate enough variation for natural selection to have anything to work with. And then you need environmental pressure to select for specific traits. And then you need time, lots of time, for those traits to accumulate, spread through the population, and become fixed. The transition from fully aquatic fish to fully terrestrial tetrapods took approximately 70 million years. That's 70 million years of drought cycles, predation, starvation, disease, and reproductive failure. 70 million years of creatures being born with bodies that didn't quite work, struggling to survive, mostly failing, occasionally succeeding just enough to pass their genes forward. And during all that time, the vast majority of species that attempted this transition went extinct. We know of maybe a dozen transitional forms from the fossil record, but that's because fossilization is rare. For every fossil we find, there might have been hundreds or thousands of species that lived and died without leaving any trace. Soft tissue doesn't fossilize well. Small populations don't fossilize well. Species that only lasted a few thousand years might never appear in the geological record at all. So the survivors, the lineage that eventually led to amphibians, reptiles, mammals, and you, they weren't the best designed organisms. They weren't the smartest or the strongest or the most deserving. They were just the ones that happened to survive. Maybe they lived in an area where droughts were frequent enough to favor terrestrial adaptations, but not so severe that everyone died. Maybe they had a lucky combination of mutations that, while individually mediocre, worked together just well enough. Maybe they avoided predators by chance. Maybe they didn't get infections from their cracked skin. Maybe their eggs happened to be laid in a pool that didn't dry up that year. Luck. That's a huge component of evolution that doesn't get emphasized enough. Skill matters, traits matter, but so does being in the right place at the right time. A perfectly adapted organism can go extinct if an asteroid hits, or if the climate shifts too rapidly, or if a new predator arrives. Meanwhile, a mediocre organism can thrive simply because it happened to be in a region that was spared the worst of whatever catastrophe occurred. Your lineage survived. There were probably multiple points in those 70 million years where the entire line nearly went extinct. A particularly bad drought, a new predator, a disease. Any of those could have ended it, and if it had ended, you wouldn't exist. None of your ancestors would exist. Humans, all mammals, all terrestrial vertebrates, gone. The planet would have continued, life would have continued, but it would have taken a completely different path. That's the humbling reality of evolutionary history. You're here because of an unbroken chain of survival, stretching back hundreds of millions of years through every extinction event, every climate change, every predator encounter. And that chain was broken for countless other lineages. The trilobites, the placoderms, the early tetrapods that didn't make it, they all tried just as hard, struggled just as much, and failed anyway. So when you look at your hands, at the 5 fingers that are standard for terrestrial vertebrates, Remember that 5 is arbitrary. Some early tetrapods had 6, 7, or 8 digits. 5 just happened to be what the surviving lineage settled on, and once it was established, it became the template. Not because 5 is optimal, but because changing it would require re-engineering the entire limb development process, and evolution rarely does that once a structure is established. The survivors weren't perfect. They were just good enough, in the right place, at the right time, with enough luck to make it through, and that's all evolution ever requires. Not perfection, just survival. And now, after 13 chapters of suffering, struggle, and near constant failure, let's talk about what all of this cost. Because the bill for growing legs was steep, and it's still being paid in ways you might not realize. So what did it cost? What was the actual price of this transition from water to land, from fins to legs, from gills to lungs? Let's tally it up, system by system, because the invoice for terrestrial life is written in suffering, compromise, and biological patches that still haven't been fully resolved 375 million years later. First, the spine. Your spine right now is a marvel of engineering, but it's also a disaster. It's trying to be both a flexible swimming apparatus and a rigid weight-bearing beam, and it fails at both. You get back pain. Everyone gets back pain eventually. That's because your vertebrae are stacked in a curve that's constantly under compression from gravity. Discs herniate, vertebrae degenerate, nerves get pinched, and all of this traces back to a spine that was originally designed to flex side to side for swimming, not support weight vertically. Engineers, if they were designing a terrestrial animal from scratch, would never build a spine like yours. They'd use something more like an arch bridge, with compression distributed through curved supports. But evolution can't start from scratch. It has to modify what's already there. So you're stuck with a spine that's pretty good at swimming, pretty good at walking, and perfect at neither. The cost: chronic pain for millions of humans, slipped discs, degenerative conditions, and a lifetime of chiropractor visits. Next, the respiratory system. You have lungs now, yes, but they're not as efficient as they could be. Bird lungs, for example, are far superior. Birds have a flow-through system where air moves in one direction constantly, extracting oxygen on both inhalation and exhalation. Your lungs are dead-end sacs. Air goes in, air goes out, and the deepest parts of your lungs never fully exchange their air. That's why you can't extract oxygen as efficiently as a bird can. That's why you get winded more easily. And your lungs are vulnerable. Pneumonia, bronchitis, asthma, all of these are diseases that exploit the fact that your lungs are moist, warm environments connected directly to the outside world. Fish don't get pneumonia. Their gills are constantly flushed with water, making infection harder. But your lungs? They're perfect breeding grounds for bacteria and viruses, and your immune system has to work constantly to keep them clear. The cost: respiratory diseases that kill millions of people every year. Then there's your heart. You have a 4-chambered heart now, which is a huge improvement over what Tiktaalik had, but it's still not perfect. Your heart has to pump blood upward against gravity every single beat. That requires high blood pressure, which is fine when you're young and your arteries are flexible. But as you age, high blood pressure damages your blood vessels, leading to atherosclerosis, heart attacks, strokes. Fish don't have heart attacks. Their blood pressure is low, their hearts are under less stress. Your heart is working overtime every moment of your life because it has to overcome gravity. The cost: cardiovascular disease, the leading cause of death in humans. Let's talk about your ears. Those tiny bones in your middle ear, the malleus, incus, and stapes, they're modified gill arch bones. They work pretty well for hearing airborne sound, but they're also fragile. They can be damaged by loud noises, infections, or just aging. And because they're repurposed structures, they're not optimally designed for their current function. An engineer designing an ear from scratch would use different materials, different shapes, but evolution had to work with modified fish bones, and the result is good but not great. The cost. Hearing loss affects nearly half of people over 65. Your sinuses. Oh, your sinuses. These are spaces in your skull that in fish help reduce the weight of the head and provide buoyancy. In you, they're just hollow cavities that trap mucus and get infected. Sinus infections, sinus headaches, chronic sinusitis. All of these are problems that exist because your skull is still carrying around fish architecture that serves no useful purpose on land. The cost. Your eyes. You have eyelids and tear ducts now, which is great, but your eyes still dry out easily if you don't blink enough. You can get infections, your vision degrades with age, and your eyes are still fundamentally aquatic organs that have been modified to work in air. The lens has to be stronger to compensate for air's different refractive index, and that makes it less flexible, which is why most people need reading glasses as they age. The cost. Nearly everyone over 50 has some form of vision impairment. Your skin. You have skin that's waterproof, mostly, but it still needs constant maintenance. You have to stay hydrated or your skin cracks and bleeds. You have to protect it from sun or you get burns and cancer. Your skin harbors bacteria, fungi, and mites that cause infections and conditions. And unlike fish scales, which are hard and protective, your skin is soft and easily damaged. The cost. Skin conditions affect nearly everyone at some point, and skin cancer is one of the most common forms of cancer. Your reproductive system. You have internal fertilization now, and eggs that can develop on land, which is a massive improvement. But childbirth in humans is uniquely difficult because of the conflict between upright posture, which narrows the pelvis, and large brains, which require babies to be born with big heads. That combination makes human childbirth dangerous and painful. For most of human history, childbirth was one of the leading causes of death for women. The cost. Even with modern medicine, hundreds of thousands of women die in childbirth every year globally. Your joints, your knees, hips, ankles, shoulders, all of them are under constant stress from bearing weight and moving against gravity. Arthritis is almost inevitable if you live long enough. Your cartilage wears down, your ligaments stretch and tear. Your bones develop spurs and deformities. Fish don't get arthritis. Their joints are designed for movement in a supportive medium. Yours are designed for weight bearing, and they wear out. The cost. Joint problems affect the majority of elderly humans, limiting mobility and quality of life. Your circulatory system. You have varicose veins because blood has to fight gravity to return from your legs to your heart. You have hemorrhoids for the same reason. You get dizzy when you stand up too fast because your blood pressure regulation isn't perfect. These are all problems that stem from being a vertical animal with a circulatory system that evolved horizontally. The cost. Vascular problems, clots, strokes, and a whole category of cardiovascular issues tied to posture. And let's talk about energy. You burn calories constantly just to maintain your body temperature. you need to eat far more food than an ectothermic animal of equivalent size because your metabolic furnace is always running. That's great for staying active in different temperatures, but it means you're always a few days away from starvation if food runs out. Fish can survive weeks or months without eating. You can't. The cost. You're a slave to your metabolism, constantly needing fuel, constantly eating, constantly dependent on a steady food supply. Add it all up, and the picture is clear. Terrestrial life is a collection of compromises, patches, and inherited problems from aquatic ancestors. You're not optimally designed for land. You're a fish that's been heavily modified, and those modifications are good enough to work, but they're far from perfect. Every chronic condition, every structural weakness, every system that breaks down with age, it's all a result of trying to adapt an aquatic body plan for terrestrial life. Was it worth it? That's not really a question evolution answers. It happened. It worked well enough for the lineage to continue. And here you are, 375 million years later, dealing with back pain and sinus infections because a fish once decided, or rather, was forced by circumstance, to crawl out of a drying pool. But despite all the costs, despite all the suffering and failure and compromise, there's something remarkable about the fact that it worked at all. And maybe, just maybe, there's something worth celebrating in that. Let's talk about that next. So here you are, lying in bed, breathing air without effort, your heart pumping blood efficiently to every part of your body, your spine supporting you comfortably against a mattress designed specifically for your terrestrial anatomy. You're warm or cool, whatever you prefer, because you have climate control and blankets and the ability to regulate your own temperature. You're safe from predators. You're not starving, your skin isn't cracking, and you're probably not thinking about any of this because it all just works automatically, without conscious effort. But every single one of these things, every breath, every heartbeat, every degree of body temperature you maintain, is the result of 375 million years of evolutionary struggle. Every comfort you experience right now was paid for by countless generations of creatures that suffered, failed, and died so that their descendants could be slightly better adapted. You are the end point, at least for now, of the longest, most brutal endurance test in the history of life on Earth. Think about breathing. Right now, air is flowing into your lungs, oxygen is diffusing into your bloodstream, and carbon dioxide is being expelled, all without you thinking about it. Your diaphragm contracts and relaxes in a rhythm controlled by your brainstem. Your ribcage expands and compresses. Your blood carries oxygen to your brain, keeping you conscious, keeping you thinking. This entire system exists because a fish 375 million years ago gulped air from the surface of a dying pool and survived long enough to reproduce. That fish's lungs were terrible. They barely worked, but they worked just enough, and over millions of years, through countless generations of incremental improvements, those terrible lungs became the efficient, sophisticated organs you have now. Every breath you take is a testament to that long, painful process. A process that killed more individuals than it saved, but saved just enough to continue the line. Think about your legs. Right now, they're probably stretched out, relaxed, resting. Tomorrow, you'll stand up, walk to the kitchen, maybe go for a run, all without thinking about the biomechanics involved. Your femur, the strongest bone in your body, will support your full weight without breaking. Your knee joint will bend and extend smoothly. Your ankle will absorb impact and provide stability. This entire system exists because a fish with slightly thicker fin bones managed to drag itself to another pool and lived to reproduce. Those proto-legs were clumsy, weak, prone to breaking, but they were better than nothing. And over millions of years, through endless iterations of failure and slight success, they became the powerful, articulated limbs you use every day without appreciation. Every step you take is built on a foundation of broken bones and exhausted muscles from ancestors who barely survived the attempt. Think about your heart. Right now, it's beating steadily, around 60 to 70 times per minute if you're resting. It's pumping oxygenated blood to your brain, your organs, your muscles. It's maintaining blood pressure, adjusting to your position, compensating for gravity. This four-chambered marvel exists because simpler hearts, two-chambered and three-chambered, weren't quite efficient enough, and the creatures with slightly better hearts survived slightly more often. Your heart will beat roughly 2.5 billion times in your lifetime. Every single beat is powered by a system that evolved from a fish heart that could barely handle the stress of life between water and land. Every beat is a reminder that evolution doesn't create perfect solutions. It creates solutions that are good enough, and then, over time, brutal process of killing off the individuals with worse versions. Think about your skin. Right now, it's keeping water in and pathogens out. It's regulating temperature through sweat glands. It's providing sensory information about pressure, temperature, and pain. It's healing itself constantly, replacing dead cells, fighting infections, maintaining its integrity. This entire system exists because fish skin, thin and permeable, wasn't good enough for land, and the creatures with slightly tougher skin survived slightly more often in the harsh, dry air. Your skin will shed roughly 40 pounds of dead cells over your lifetime. Every cell that's replaced is part of a system that's been under development for hundreds of millions of years, solving the problem of how to keep a body intact in an environment that's constantly trying to dry it out. You are not separate from this history. You are not observing it from the outside. You are it. Your body is a living museum of evolutionary compromises, carrying structures that were designed for aquatic life and modified, imperfectly, for terrestrial existence. Your ear bones used to be gill supports. Your spine used to be a swimming organ. Your lungs used to be a swim bladder. Every part of you tells a story of transformation, of adaptation, of survival against overwhelming odds. And here's the thing that's easy to forget in the comfort of modern life. You almost didn't exist. Not you personally, but your entire lineage. There were multiple points in those 375 million years where the line could have ended. A drought that was too severe. A predator that was too successful. A disease that spread too quickly. Any of those could have wiped out your ancestors before they reproduced, and if that had happened, you wouldn't be here. None of your family would be here. Humans wouldn't exist. But it didn't end. The line continued. Through extinction events that killed 90% of species. Through climate changes that transformed entire continents. Through competition, predation, disease, and random bad luck. Your ancestors somehow made it through all of that. Not because they were the strongest or the smartest or the most deserving, but because they were just lucky enough, just adapted enough, just in the right place at the right time. So, tonight, as you drift off to sleep, as your breathing slows and your heart rate drops and your body enters its restorative cycle, take a moment to appreciate the sheer improbability of your existence. You are the descendant of fish that learned to breathe air, of fish that grew legs and walked on land, of creatures that survived droughts, predators, and environmental catastrophes that would terrify any modern human. You are the product of the toughest, luckiest, most persistent lineage in the history of life on Earth. Every cell in your body carries the genetic memory of that struggle. Every system in your body is a solution to a problem that nearly killed your ancestors. And every breath you take, every heartbeat, every moment of comfortable existence is a gift paid for by unimaginable ancestral suffering. So sleep well, rest easy, and remember that you're here not because life is easy, but because your ancestors endured when it was impossibly hard. They crawled out of dying pools. They gasped for air with primitive lungs. They dragged themselves across hostile land on limbs that barely worked. They froze and overheated and starved and suffered, and they survived. Just barely, just enough. And that's why you're here tonight, comfortable and safe, drifting off to sleep in a world those ancient fish could never have imagined. A world where breathing is easy, where walking is effortless, where survival is no longer a daily battle. You've inherited their struggle, but you've also inherited their victory, and that's something worth closing your eyes and being grateful for. As you let sleep finally take you, 375 million years removed from the fish that started it all. Good night, and thank you for joining me on this journey through time. If you enjoyed this deep dive into evolutionary history, consider liking and subscribing, and let me know in the comments what topic you'd like to explore next. Sweet dreams, and remember, you're the descendant of the toughest fish that ever lived. So we've come to the end of our journey. 375 million years, 15 chapters, and one long, brutal, evolutionary transition from water to land. From fish to something that wasn't quite fish anymore. From fins to legs, from gills to lungs, from a life of buoyant ease to a life of crushing gravity and constant struggle. And through it all, one truth emerges. It absolutely sucked to be a fish growing legs. But here's what we learned. We learned that evolution isn't a story of progress or improvement. It's a story of survival under impossible circumstances. Those fish didn't grow legs because they wanted to conquer new territory or because they had some grand vision of the future. They grew legs because staying in the water meant certain death, and crawling onto land meant probable death, and probable was better than certain. That's it. That's the entire calculation. We learned that every system in your body, every structure you take for granted, is the result of millions of years of trial and error, mostly error. Your lungs aren't perfect because they evolved from swim bladders that were never designed for breathing. Your spine isn't perfect because it evolved from a swimming apparatus that was never designed for bearing weight. Your heart isn't perfect because it evolved from a two-chambered fish heart that was never designed to pump blood against gravity. And yet, they work. Not perfectly, not optimally, but well enough. And well enough, in evolutionary terms, is all that matters. Well enough means you survive to reproduce. Well enough means your genes continue. Well enough means the line doesn't end with you. And over millions of years, well enough becomes better, becomes more refined, becomes the sophisticated systems you have today that let you walk, breathe, think, and sleep without conscious effort. We learned that survival isn't about being the best, it's about being good enough, in the right place, at the right time, with enough luck to make it through. The fish that survived weren't necessarily stronger or smarter or more adaptable than the ones that died. They were just lucky. They happened to have the right mutations, They happened to be in pools that didn't dry up completely. They happened to avoid predators. They happened to find food. They happened to reproduce before something killed them. And we learned that the cost of terrestrial life is still being paid. Every back pain, every heart attack, every sinus infection, every joint problem, every respiratory condition, all of these trace back to a body plan that was designed for water and modified for land. You are not optimally designed for the life you're living. You're a fish that's been heavily modified, and those modifications are impressive but imperfect. The patches show. The compromises are visible. The evolutionary history is written in every ache, every weakness, every system that breaks down with age. But despite all of that, despite all the suffering and failure and compromise, there's something profound about the fact that it worked. Against overwhelming odds, against massive environmental pressure, against the simple statistical reality that most mutations are harmful, life found a way, not through intelligence or planning or design, but through the simple, relentless logic of reproduction. The ones that survived had offspring, the ones that didn't. And over enough generations, that simple rule transformed fish into amphibians, amphibians into reptiles, reptiles into mammals, and mammals into you. You are the endpoint of that process, at least for now. You are the result of an unbroken chain of survival, stretching back not just 375 million years to Tiktaalik, but billions of years to the first self-replicating molecules. Every ancestor you have, every single one, from fish to mammal to primate to human, survived long enough to reproduce. That's a perfect record. A single failure anywhere in that chain, and you don't exist. So when you think about sleep tonight, when you close your eyes and let your body enter its restorative cycle, remember what sleep actually is. It's a vulnerable state. You're unconscious, defenseless, unaware of your surroundings. For most of evolutionary history, sleep was dangerous. Predators hunt at night, threats emerge in darkness. Sleeping meant taking a calculated risk that you'd wake up at all. But you sleep anyway because you have to. Your brain needs to process memories, consolidate learning, clear metabolic waste. Your body needs to repair tissue, regulate hormones, restore energy. Sleep isn't optional. It's a biological necessity, and the fact that you can do it safely, in a warm bed, in a secure environment, protected from predators and environmental extremes, is a luxury that almost no organism in the history of life has enjoyed. Your ancestors slept in mud, in shallow water, in cramped burrows, always alert, always ready to wake and flee. They slept in trees to avoid ground predators. They slept in caves to avoid the elements. They slept in groups for protection. They slept poorly, their rest constantly interrupted by threats real and imagined. And they pass down to you the nervous system that makes deep, restorative sleep possible when conditions are safe, and that same nervous system that keeps you alert when conditions aren't is less than #0. 7# is greater than. The fact that you can lie in bed tonight, relaxed and comfortable, and drift into unconsciousness for 8 hours without fear, is the result of millions of years of evolutionary success. You are safe enough to sleep, you are fed enough to sleep, you are warm enough to sleep, and your body knows this, signals this, allows this, because your ancestors, through countless generations, built a world where sleep could be safe. So, as you close your eyes tonight, as your breathing deepens and your heart rate slows, as your conscious mind fades and your unconscious mind takes over, remember the fish. Remember Tiktaalik, struggling in a drying pool, gasping for air, dragging itself across mud with fins that weren't meant for land. Remember the suffering, the failure, the millions of dead ends and extinct lineages that didn't make it. And remember that you're here because that fish and all its descendants refused to give up, not consciously, not heroically. They just kept trying to survive, one generation at a time, and somehow, improbably, impossibly, they succeeded, and their success is your existence. You are not separate from evolutionary history. You are its continuation. Every breath you take uses lungs that evolved from that fish's swim bladder. Every step you take uses legs that evolved from that fish's fins. Every thought you think uses a brain that evolved from that fish's simple nervous system. You are, quite literally, a modified fish. A fish that learned to walk, to breathe air, to think complex thoughts, to dream. And tonight, as you dream, you're doing something that fish could never do. You're processing information, consolidating memories, exploring possibilities, all in the safety and comfort of sleep. That's the gift your ancestors gave you. Not just survival, but the capacity to rest, to recover, to dream of futures that haven't happened yet. So sleep well, dream deeply, and when you wake up tomorrow, take a moment to appreciate the sheer improbability of your existence. You are the result of the longest, most successful survival story ever told. You are the descendant of creatures that endured the impossible and made it look inevitable in retrospect. If you enjoyed this journey through evolutionary history, hit that like button. Subscribe if you want more deep dives into the biological stories that shaped the world we live in. And drop a comment letting me know what you'd like to explore next. Maybe the evolution of sleep itself, maybe the development of consciousness, maybe the story of how a shrew-like mammal survived the asteroid that killed the dinosaurs and eventually became you. Let me know. I love hearing what sparks your curiosity. And here's a question to take with you into your dreams tonight. If it took 375 million years and countless failures just to get from water to land, just to develop the basic systems that let you walk and breathe, about the power of small changes over long periods, about the importance of simply not giving up, even when success seems impossible. Your ancestors didn't know they were building toward you. They were just trying to survive one more day. But day by day, generation by generation, they built something extraordinary. They built you. And maybe that's the real lesson here. You don't need to see the destination to start the journey. You just need to keep going. Good night. Sleep well. And thank you for letting me share this story with you. Remember, you're the descendant of the toughest, luckiest, most persistent fish that ever lived. And that's something worth dreaming about.